I'll be talking about Pandora's problem with non-obligatory inspection. This is a joint work with Bobby Kleinberg. The problem that we study is the sequential search problem. In the sequential search problem, there's a searcher who wants to select one out of n alternatives, and evaluating each alternative comes at a cost. For example, when a firm wants to hire an employee, they can interview each candidate, and that interview process is costly. Also, when students want to select colleges, they can pay the cost to visit a college and evaluate the college before going to it. Weitzman formalized this model in 1979. In Weitzman's model, the searcher Pandora has access to n closed boxes. Each box has a price inside it that comes from distribution Fi. And there's a cost to open box I. We call it Ci. The distribution and the cost are known to the searcher in advance, but the price inside the box is not. The searcher can open as many boxes as they like in any sequence that they like, but they can claim at most one prize. And they can only claim the prize of an open box. The goal here is to design a policy that maximizes the expected value of the prize minus the costs paid to open the boxes. Weitzman solves this problem in 1979 and gives the optimal solution that I will present to you on the next slide. We study a different variation of the problem. We actually relax the last assumption, and we let the searcher to claim a box without opening it. Our main result is a 1 minus 1 over E approximation. Back to the Weitzman model. Let's see an example of what decisions are involved in a policy. Let's say the searcher here, a policy given past history, decide which box to open next, or to terminate the search and be happy with the prize that they got. For example, the searcher here can start with opening the blue box and see a value of 10 inside it. Then, based on what they saw, they might proceed to open the red box and see a value of 8. And maybe at this point, they are happy with the price that they saw, and they think that it's too costly to open the brown box and it's not worth it. So in this case, they're going to get the maximum price that they've seen, here 10, and pay the cost to open the blue box and red box, which is C blue plus C red. Okay. Since this is a profit inequality session, I want to quickly point out the differences between this problem and profit inequalities. Compared to profit inequalities, the decision here is not immediate. Like in this example, we could go back to the value of 10 that we saw previously. Also, unlike the classic profit inequality, the searcher can select the order. And there are costs involved in realizing the values. Okay. Weitzman surprisingly shows that the optimal policy has a very simple structure. In the optimal policy, a reservation value is assigned to each box. The reservation value is only a function of the distribution and the cost of the box. And you can see the formula for the reservation value on the slide, but it's not important to remember it for this talk. The optimal policy approaches boxes in decreasing order of their reservation values. For example, here the blue box has a reservation value of 15, red has 11, and brown has 9. So this is going to be the order that we open the boxes. We are going to continue the search until the highest price that we have seen so far, here 10, exceeds the next reservation value, here 9. So at this point, the searcher is not going to open any boxes further. What is important about the optimal policy is that the order of opening boxes does not depend on past history. So based on what we saw, we might decide to continue the search or stop the search, but we're not going to change the order of opening the boxes. So this is very interesting, but in many real-life applications, the search is not obligatory and it's optional. And we sometimes take paths without exploring them first. For example, a student can select a college without visiting it. So we're going to change the model a little bit and let the searcher acquire a closed box without opening it. And in this case, the searcher is going to get the expected value of the box. This problem was introduced to the research community by Doval. There is also interesting work by Hedyeh and co-authors who study some aspects of the problem. Among other things, Doval showed that there are examples where the optimal policy can be complex. So let's see some examples of that. This example shows that Pandora's rule, the optimal rule in Weitzman model, might not be optimal in the new model. Let's say we have two boxes. Box 1 has value 0 or 1 with equal probability. Box 2 has a huge value of n with probability only 1 over n, and it's 0 otherwise. The cost is a half. In the Weitzman model, the reservation value of box 2 is bigger. But here, the optimal policy is to open the first box first. We're going to open the first box. If the value inside it is 0, we're going to acquire box 2 without even opening it. If the value is 1, we're going to open the value of the box 2 and pick the maximum value that we saw. The optimal policy gives a value approaching to 5 over 4, but pre-committing to open box 2 or keeping it closed gives at most a value of 1. Here's another example that shows the optimal policy could be complex. We're keeping the same two boxes. We're boosting the cost of box 1 to epsilon. And there's now box 3 that has values n squared, 1, or 0. The optimal policy here is to open box 3 first. If the value is n squared, we're going to stop the search. But something interesting happens if the value of box 3 is not n squared. If the value is 1, we should open box 2 next. But if the value is 0, we should open box first next. So here we see that unlike the optimal policy in the Weitzman model, opening the boxes, the order to open boxes depends on the past history. So these kind of complexities in the optimal policy motivate the study of approximation algorithms. And our main result is a 1 minus 1 over e approximation to the optimal policy. We design a simple policy that gives this approximation. For the most of the remaining part of the talk, I'm going to give the high-level ideas of the proof. First, I'm going to define a related problem. Singla studies and introduces many problems under a Weitzman model with probing constraints. In these kind of problems, inspection is obligatory, meaning that you need to first open a box to acquire the prize inside it. But there is a constraint on the set of boxes to open. And for an example, the opened boxes should satisfy a mate rate constraint. Our first step of the proof is a reduction from our problem to a problem of this kind. One key observation for the reduction is that in any simulation of a policy, for any box I, we're going to either select to open box I or acquire it closed, and we cannot pick both of these. Therefore, equivalently, we can treat each box as a pair of boxes. In the first pair, we're going to have a box with the same distribution of fi and cost ci, but the second copy is going to have the deterministic value, which is the expected value of the prize, and a cost of 0. And the idea is only to open one of them, but we cannot open both. So I summarized this step in the table on the right, and each row corresponds to box I. Now we have two copies of each box. On the left, we have the closed version, and on the right, we have the two open version with the distribution of the prizes and the costs that you see. The next step is to think about the restrictive problems that we already know the optimum solution to it. We define a committing policy of a policy that selects from each row at most one element and pre-commits not to open the other box in the row. And you can see, for example, a selection in the table on the right. And the key observation here is that given a selection, the optimal committing policy is Pandora's rule. And the main question from here on is going to be, can any committing policy approximate the optimum? The last step of the proof is a reduction to a problem with no cost. We show that we can modify the distributions of the two open boxes to modify distributions of GIs, again, and no cost. Again, the formula is on the slide, but it is not important to remember it. So in this step, the problem of maximizing the expected value of the price minus the costs reduces to a pure maximization problem. In previous papers, they proved the reduction for the obligatory inspection case, and this is a more generalized reduction that also holds for the non-obligatory inspection case. So here, basically, the committing policies correspond to non-adaptive strategies in stochastic maximization, and the optimum policy can be an adaptive strategy in stochastic optimization. And we're using the adaptivity gap by Asadpour and Nazarzadeh to give a 1 minus 1 over E approximation. The constraint that we have here is a matrix partition constraint because in each row we can select at most one box. And by their result, we know that the non-adaptive policy, which corresponds to committing policies here, is at least 1 minus, the best of them is at least 1 minus 1 over E approximation to the optimal adaptive policy. So now we know that there exists a policy of that gives 1 minus 1 over E approximation, but what is that policy? The main observation that limits the set of optimal policies is that we need at most one closed box. When we have multiple closed boxes, the one that has the higher value is going to dominate the other boxes. So the optimal committing policies is going to be one out of these n plus 1 policies. We're going to define P superscript I, the committing policy with closed version of box I and open version of other boxes. And we're going to show that one of these n plus 1 policies, one that doesn't have any closed copy and the other ones that have only one closed copy, gives a 1 minus 1 over E approximation to the optimal policy. This approximation is not tight, and we're still working to improve it, but we managed to find an improved approximation for the case of 2 boxes. We show that for the case of 2 boxes, the same policy gives a 4 over 5 approximation. And this approximation is tight, and you can see in the example, this is the first example that we saw in this talk. Here, the best committing policy achieves a value of 1, but the optimal policy achieves a value of 5 over 4. And this shows that our result for the 2 boxes is tight. I'm going to conclude now. In summary, we found our main result is a 1 minus 1 over E approximation to the sequential search problem with non-obligatory inspections. The main proof techniques that we used was, one was a reduction from the sequential search problem to a pure optimization problem. And the other one was the adaptivity gap from submodular optimization. For the future directions, we showed in a subsequent unpublished work, we showed that 1 minus 1 over E can be improved. We're still working to see if we can improve the new bounds. So one question is, how powerful are committing policies, and what is the best approximation guarantee that we can get with them? Is it going to be 4 over 5, like the example we saw, or is it going to be less? Another open direction is to find mechanisms for the environments with non-obligatory inspection. So we can see what happens in the auction version of the problem when there are strategic agents, but still they have to solve this sequential search problem. There's a related work by Azevedo, Panak, and Weil, but they don't yet have price of anarchy results. Another question is to think beyond committing policies and see if there exists any p-test for the problem. And I think Singla and Wang already showed in a non-published work that it is possible. Thank you for listening, and I'm happy to take questions.
So I'm wondering if there's any hope that a simple Weitzman-style descending strategy with maybe some small modification could still get a constant factor or something.
Yeah, we haven't worked on it, but I also think it could be possible to get a constant approximation in that setting.
I was wondering, it seems to me when you're opening boxes that you're assuming risk neutrality.
That's right.
Yeah, but it seems to me like, if I go in college or something, that tends to be a little more risk averse. And so I need to look at that.
Right. So something that I didn't show in this talk is that we actually solve a more general type of the problem. In that problem, you can treat each box differently. So we showed two versions, either to open the box and claim the price inside it or take the box closed. But for example, when you want to hire an employee, you can think of either giving them an internship, doing an interview process, or just hire them. So there could be these intermediate steps that are less costly but refines the distribution a little bit. So our work generalizes to that setting as well.
Otherwise, let's thank all the speakers for the session.